All right, this video is on the class problem special cases of circular motion, typically for people who are absent or if you just want to see them again. All right, so I am on our workbook, page 5. Workbook, page 5. Okay, so we're going to start off with number 1. We are turning corners. Turning corners here. So if, maybe it'll let me actually do this. Take a screenshot. Okay. We'll take a screenshot of this problem, copy it over to where I can actually work on the problems. All right. If we are turning a corner, let's say we're in a car, turning a corner, the only thing that is letting us turn that corner, right, if it is the tires, right? If we have a car, let's say this is a rear view. Let's say we're in the rear view. There's our car, because I'm a great artist. Let's say this is the rear view. There's the road, and we're wanting to turn to the right. Well, what's the only thing pushing it to the right? There's nothing really pushing it, but the only thing actually pushing it is the friction between the tires and the road. Is that friction there? So when I do this, the sum of the forces toward the center, right, mv squared over r, we've kind of gone over that already, but the only thing letting us turn is the force of friction. It's kind of interesting. So if we were to draw a free body diagram on this, right, we've got gravity and normal force. So that's just kind of regular, and then friction, force of friction is there pushing us in toward the right if we're making a right-hand corner. We will just always kind of simplify these by saying that we're moving in a circle. There's the center of the circle. Okay, here's our car is just right here, and our car is trying to turn this away, but the force on the car is that way, right? That's the force of friction. Okay. So, and this is, right, that's the radius of our turn. The car is moving at some velocity v, and that's what your speedometer would tell you. Okay, so we've got this expression now, this Newton's second law expression for the sum of the forces toward the center on this car, the only one of which being friction. So if we're to move along down the process here, right, mv squared over r, but what is force of friction? Well, it's mu Fn. But if we look at our free body diagram, right, normal force is going to equal force of gravity, because those are the only two forces in the vertical axis, which is just mg. Okay, so we plug that in for our normal force there. That tells us mv squared over r equals mu mg. Real fast, as a quick aside, what type of mu is this? What type of friction? Well, if the wheels are rolling, are they sliding? No, they're not sliding. So even though it's moving and our base assumption is kinetic friction, it's not sliding, right? Kinetic friction happens when something is actively sliding, whereas mu static happens when we're trying to prevent something from sliding, which is what happens when we roll. You got to remember that. Okay, that was just an aside. That doesn't really truly matter to the problem. But, all right, so we're down to this point now. Well, there's mass on each side, so we can cancel that. Since there's a mass in every term, we can cancel mass, which just leaves us with v squared over r is equal to mu static times g, or 10. All right. Well, I'm asking in this problem, what is the minimum turning radius they can make? So that means we're looking for r. We're looking for radius. And minimum turning radius is just how small can the circle be. Okay, so we're looking for r. To do so, all right, let's multiply by r on both sides. So times r. So we'll get this v squared equals r mu static g. I just want to, I'll stop writing mu static for a moment. I just want to take a slight aside here. Take an aside and say, okay, if we want to ever find the velocity that a car is moving at, right, this is just v squared, or the velocity that a car can turn a corner of some radius r with some coefficient of friction mu on some planet with gravity g, you find the maximum velocity it can take that corner under the rug, right? Under square root and then rug r mu g. That's just an aside. You can just remember that, because what's kind of cool is on the AP test, now that we've kind of done this whole process, you can start here. Start with this Newton's second law expression. Now that we've done this, if you just remember this velocities under the rug, then you can go straight there. You've got to write this Newton's second law expression because that recognizes, or that shows that you recognize this is a forces problem and that this is a circular motion problem with the v squared over r. And it shows that you recognize force of friction. And it shows that you recognize that force of friction is mu times mg because you go straight down to mu and g, but mass is canceled. So you've got to do this Newton's second law expression. But once you've done that, feel free to go straight to velocity is under the rug. Okay. But this problem I'm asking you about r. I'm asking about the radius. So when we get to here, instead of solving for velocity, we're going to solve for radius, which means, right, over mu g over mu g. So our radius is going to be v squared over mu g. Okay, then the problem, I believe, has some numbers here. So our radius is going to equal velocity. We're moving at 24 meters per second. So 24 squared over coefficient of friction is 0.64. So mu is 0.64. And then g, always 10, at least on Earth. I don't know of any other planets that have cars. So, okay. And then if I get this calculator pulled up here. Here we go. So there's our calculator. We've got 24 squared over 0.64 over 10. All right, we have to divide by those again. We have to divide by this since they're both on the bottom if I don't want to type in the parentheses. So that gives me 90. All right. Turning radius is 90. And it's a radius, which is a distance, so 90 meters. Okay. So a couple of important things to note here. One, Newton's second law. All right, so that's our sum of the forces expression toward the center. Second thing to note, it's mu, static. Third thing to note, you find the maximum velocity that a car can make a corner under the rug. What this tells us is that the bigger the turning radius gets, the faster you can take the corner, right? Because it's being multiplied. The bigger your coefficient of friction is, the faster you can take a corner. That's not surprising. If you're on a planet with heavier gravity, you can take the corner faster. But let's look at it the other way. What happens if mu decreases? Let's say it's an icy day on the roads. Well, the velocity is gonna decrease. And it's a squared function because of that square root. So mu is low, drive slow. All right. I'd be remiss in my physics teacher duties if I didn't drill that into your little noggins. All right. So we can go over to number 2 now. All right. Oh, find an expression for the coefficient of friction necessary to make a corner with radius r, traveling at some speed v on a planet with some acceleration of gravity g. Okay, this is actually going to be fairly straightforward for us based on the last problem we just did. Okay, so we know that when cars turn a corner, it's basically, we're going to treat it like a circle. So the sum of the forces toward the center is mv squared over r. But what's the only thing turning it toward the center? Friction. Okay, but remember what we said last time. We could start there, but since we've already done this, we can show that we really understand this problem and just skip to, where do you find the maximum velocity? Under the rug. So we can just skip right there. You can go straight from there, and that is perfectly acceptable for the AP test. You'll earn all the points. Okay, So we can do that, but we want an expression for the coefficient of friction. So we're solving for mu. Okay, so instead of v, we're going to need v squared equals r mu g. But then we're solving for mu, so we got to divide by rg. So mu equals v squared over rg. Done. That's it. Easy as that. Oh, somehow the problem went away, but okay, so that's number 2. I don't know where the problem went on that, but all right. Feel free to stop the video, pause, go back, whatever you want, but I'm going to keep going so this video doesn't take 9.5 years. All right, vertical loops. Vertical loops. So vertical loop, we've got this little hamster. Feel free to give him a name, whatever name you want. I think I'm going to name him Gerald. Okay, so we've got Gerald, our little hamster, spinning on his wheel. He loses control. Spinning round and round and round and round and round. Okay, so our hamster, going around. Hamster make 5 revolutions every second. Just by the way, I'm going to annotate these problems. 5 revolutions every second. I'm going to annotate them just to tell me numbers. Where's the number? Okay, so assume no friction. Okay, so that just means the wheel doesn't slow down over time, which hamster wheels are actually fairly decent at, which is kind of fun. What is the normal force? What is the normal force? Okay, so that means question mark Fn. What is the normal force between the hamster and the wheel at the top of the circle and at the bottom of the circle? Wheel has radius of 10 centimeters, but that's 0.1 meters. And the hamster has a mass. Here we go. Mass of 0.056 kilograms. Boom. Okay. For right now, I'm going to take a moment aside from the problem and just look at what's going on in this situation. All right, so let's say our little hamster is right over here. Hamster, tail, feet, 4 legs, I guess, ears. Let's say he's right there. What forces are acting on Gerald at the bottom of the wheel? Well, we've got the force of gravity. It's always a good place to start. But then the normal force of the wheel to the center. But what if Gerald's on the side over here? I'm just going to do a blob because I'm bad at drawing anyway. Well, we've got the force of gravity acting down. Force of gravity, but then normal force, right? The wheel is on the left side of Gerald, so that means it must push Gerald to the right. Normal force. What if Gerald's up top? Well, we've got force of gravity, always down. But we've also got the wheels above him, which means the wheel's pushing him down too. Normal force. Then over here, one last side, well, force of gravity pulls down. Force of gravity pulls down. Normal force, the wheel's on his right, so it pushes him left. Sorry, not gravity, normal force. Okay, so what this tells us, right, because whenever we do these expressions, we care about the sum of the forces toward the center, right, which is mv squared over r. We care about those toward the center. On the sides, right, the center is over here. That's the center of our circle. On the sides, gravity is completely opposite, or it's completely perpendicular to the circle, or from the point to the center. So that means on the side, we don't care about gravity whatsoever. It doesn't affect our circle. However, on the bottom, right, normal force is pushing him toward the center, but gravity is pulling him away from the center. So on the bottom, not only does the normal force have to overcome gravity, but it also has to push him toward the center also. That's why I drew my arrow for normal force longer than the arrow for force of gravity here. So let's take a look at, one more thing. Then on top, normal force is down toward the center, but gravity is also down toward the center, so they work together. That means normal force is less. That's why if you've ever ridden a roller coaster, when you go around a loop-de-loop, at the bottom, you feel like the roller coaster is pushing into you so much more than at the top, because at the top, normal force and gravity work together to help you make that circle. But at the bottom, normal force and gravity oppose each other. So the roller coaster has to push you up even harder. But then at the top, the roller coaster doesn't have to push you in toward the center very hard because gravity's helping out. Okay. And if you haven't ridden a roller coaster, highly suggest it. You learn a lot of physics that way. All right. So let's take a look at two instances, the top and the bottom. So the top, that's going to correlate to part A on the problem. The bottom is going to correlate to part B on the problem. Okay, so at the top of the circle, the forces toward the center. That's what sum of the forces toward the center. So toward the center, does gravity point toward the center? Yes, it does. Force of gravity points toward the center, so it's positive. How about normal force? Does it point toward the center? Yes, it does. So it's positive normal force. But instead, if we look at the bottom, if we take the sum of the forces toward the center, right, mv squared over r equals, well, toward the center is normal force, so that's positive. Normal force is positive. But then away from the center is gravity, so that will be negative. Okay. So remember, since normal force and gravity, yes, they are down here, they're in opposite directions, but they don't equal each other because normal force has to win to make Gerald go in a circle, to make our little hamster go in a circle. Normal force has to win, so they don't equal each other. So what this tells us, right, mv squared over r, so at the top of the circle, force of gravity helps positive mg plus Fn. Can we cancel mass, though? Right, there's a mass in this term, but there is not mass in this term, so we cannot cancel mass. So if I'm looking for the normal force, right, which is what the question asks us to look for normal force. What is the normal force? So I'm going to solve for normal force. I'm going to subtract mg from both sides, subtract mg. Okay, so we'll have normal force. Now let's do this in a different color. Normal force is equal to mv squared over r minus mg. And this is at the top again. All right, that's at the top. But instead, if we're to do this at the bottom, right, this is minus mg. So Fn mv squared over r equals Fn minus mg. We still can't cancel mass because it's not in every term. But now, instead of subtracting mg, now we get to add mg to both sides. So this tells us that normal force will equal mv squared over r plus mg. Right? This is at the bottom. So at the bottom of the loop, normal force is going to be greater because it's plus. At the top of the loop, normal force is going to be lower because it's minus, which makes sense because right at the bottom of the loop, normal force has to push up not only toward the center, but also to overcome gravity. At the top, they work together, so normal force can be less. Okay, so part A asks, what is it at the top of the circle? What is it at the top of the circle? Well, we don't have velocity yet. We have radius, but we don't have velocity yet. What we do have is 5 revolutions per second. 5 revolutions every second. If I tell you how many revolutions per second that is, that's frequency. Frequency is in revolutions per second, and there's 5 of them. It's in units of hertz, which is just 1 over seconds. But what helps us is that period is 1 over frequency, which means this is 0.2. Don't need the parentheses, 0.2, and period is in seconds. Okay, so it takes Gerald 0.2 seconds to go around the wheel. Well, we could get velocity from that, right? By plugging in velocity is 2 pi r over t, distance over time. The other way to do it is just by plugging 2 pi r over t, plug that in for velocity right there. What that gets us actually would be m, and then this is the other version of acceleration, 4 pi squared r over t squared. Right? Remember, I told you to memorize that. I hate saying the word memorize, but I told you to memorize it. Okay, so this tells us normal force at the top of the circle. Now we can just plug in all our numbers. Okay, mass is 0.056, radius is 0.1, t is 0.2. So mass 0.056 times 4 pi squared r is 0.1 over t 0.2 squared minus mass 0.056. G is 10. All right, let's get our calculator up. Oh no, is my calculator on? Okay, 0.056 times 4 times pi squared times 0.1 divided by 0.2 squared minus 0.056 times 10. All right, I get 4.97. So normal force at the top equals 4.97. It's a force, so newtons. All right. So that's part A. That's at the top. Part B asks us, what's the normal force at the bottom? Well, you know it's fun. Part B, because we've already kind of done this. We've decided that v squared over r isn't truly helpful to us. So 4 pi squared r over t squared, that's the version of acceleration that helps us in this case, since we don't know v, but we do know period, plus mg. All right, that's our normal force. But what did we just do? We just did this exact equation, but with a minus sign. So what we could do is take all of these quantities we just did, but instead of a plus, or sorry, instead of a minus, all we have to do is plus. It's the same exact equation otherwise. So all I'm going to do on my calculator, I'm going to do second entry, because that gives us what we just typed in, and then I'm going to scroll back, and instead of the minus, I'm just going to hit plus. Enter. 6.09. So at the bottom of this loop, normal force 6.09 newtons. All right. So that's number 3. I believe number 4, if I remember correctly. Yes, derive an expression for the normal force at the top of the wheel. We already did that. That is right there. Or right here, whichever one you want. All right. And then number 5 and number 6 are on banked corners. That's something that AP doesn't really emphasize anymore. So I won't do that in this video. If you're curious about them, come find me outside of class. Happy to walk through those. But that is our video on circular motion applications. If you have questions, let me know. Otherwise, good luck. Have fun solving your problems. And I'll see you in class.